Hi guys, welcome to New Dimensions YouTube channel. Your host is Michael Mansa Dioba. I'm going to continue with matrix algebra part 2. Under this particular session, I'm glad to tell you that I'll look at how to come up with the determinant of a matrix, both a 2 by 2 matrix and a 3 by 3 matrix. We'll look at how to come up with the inverse of a matrix, both 2 by 2 and 3 by 3 matrix. We'll also come to look at how do we come up with an identity matrix of both 2 by 2 and 3 by 3 matrix. We'll conclude by looking at how do we solve the system of equations, linear equation, using matrix method. I'll introduce you to Cramer's rule as well as the inverse method. So that's what I have for you in this presentation. What is a determinant? Okay, a determinant is described as a number which is always obtained from a matrix, which is can be a 3 by 3 matrix or 2 by 2 matrix or 4 by 4 matrix, etc., etc., etc. Let's look at a 2 by 2 matrix where you have matrix A given with elements of A, B, C, and D. For you to come up with a determinant, which is characterized by the symbol of two parallel lines on both sides of the symbol for a matrix, in this case A. When you have a parallel line before A and a parallel line after A, that is symbolic of or indicative of a determinant of a matrix. And how do you do the calculation? You look at if A is the matrix A, B, C, D, then the determinant of the matrix A will be found by you multiply the diagonal matrix elements of A and D, then subtract from the diagonal matrix C and B. So we have downsloping diagonal AB, AD, those are two elements multiplying, and the upsloping diagonal C and B, that is subtracted from AD. So that's what we have in this particular case. So we look at example of a matrix A being 2, 1, 3, and 4. If we are going to find let me just come back to this one. If we are going to find what is a determinant of this matrix, a determinant of this matrix, okay, we look at that. I want to correct this one. Okay, fine. Then you're going to have 2 times 4, the downsloping diagonal elements, minus 3 times 1, the upsloping diagonal elements. So what you're going to get is 8 minus 3, which is equal to 5. Therefore, determinant of this 2 by 2 matrix is equal to 5. So we move on to look at the next one. Okay, the next one is we want to find out the determinant of a 3 by 3 matrix. If the 3 by 3 matrix is made up of elements A1, A2, A3, B1, B2, B3, C1, C2, C3, how do we calculate the determinant of this matrix? Okay, we're going to look at 2 methods. I'll start with the long one, and then I'll introduce you to a shorter one, and your choice is yours. Just to give it a flavor, let me start with this long one. Okay, first of all, you need to know that with this 3 by 3 matrix, you need to resolve what are its minors. Okay, so we need to know what is a minor. A minor is a determinant that is associated with an element in a matrix. Okay, to calculate a minor, I've indicated that a minor associated with a particular element, you need to delete the row and column in which the element lies. Okay, so for instance, if you look at element A1, this one. Okay, what we need to look at in this particular case is A1 is in this column, and also A1 is taking this particular row. So if you remove those, what you are going to have is the outlying elements of this particular line drawn is B2, B3, C2, C3. That's what you're going to have. That's what you're going to have. So now, if that's the case, then we are going to look at this element A1. This element A1, and it has B2, B3, C2, C3. So that's what we have. So the minor related to A1 is B2, B3, C2, C3. So equally, when you come to A2, what you are going to do in this particular is you remove this one, for instance. Okay, remove this one. E2 is this one, so you are going to cross out on which row is A2 found. It's in this row. And which column is A2 found? It's in this column. Okay, so now what we do in this particular case, we look at the elements that are off these drawn lines. There's B1, B3, C1, C3. So that is what is associated with the element A2. So the minor for A2 will be B1, B3, C1, C3. That is the matrix, the minor for A2. So we have in this particular card A2, B1, B3, C1, C3. That's a minor. Equally, you do the same with A3. You find the minor will be B1, B2, C1, C2. Okay, so you find the determinant relating to that. It will be B2 times C3 minus C2 times B3. Equally, you find this one, A2, there will be B1 multiplied by C3 minus C1 multiplied by B3. For A3, it will be B1 multiplied by C2 minus C1 multiplied by B2. So that's what we have. Okay, that is what we have. For B1, B2, B3, again we can isolate these minors. Okay, we can isolate these particular minors. Okay, associated with this element B1, B2, B3. Equally for C3, we can isolate the minors C1, C2, C3 as given below. So that's what you should do. That's what you should learn about what a minor of a matrix is. Okay, so now we proceed. We develop ideas about a cofactor. Once we have identified the minor, we can come up with a cofactor. A cofactor is simply a minor with a sign, either a positive or a negative. The following rules are used for allocating signs so that we come up with a cofactor, signs to the minor. So we look at the order of the element. That is what we mean by the order of the element is more like coordinate points that identify where this element sits in the matrix. So you talk about the coordinate points in this particular in respect of the row number and the column number. so rows and columns. Okay, so that's what you have. So in this particular case, if the sum of I, which is represent the number of the row, and j, which is represent the number of the column, is even, then the sign is positive to be assigned to that particular element. Okay, if the sum of I and j is odd, then the sign is negative. That's the rule which we follow. Let's look at how that is done. Okay, for instance, for a 2 by 2 matrix, the cofactor matrix will be here A1, because it is in row 1 and column 1, means I is 1, j is 1, 1 plus 1 is 2, it's an even number, so you assign a positive sign. For A2, this one, this one, it is in under, let me just put this one complete. Okay, that's fine. That's A11, meaning that in A is, this A is in row 1 and column 1. The next A is in row 1, column 2. So when you add 1 plus 2, you are going to have 3, which is odd. Therefore, the sign allocated here is negative. We come to B. B is found under row 2, column 1. Row 2, column 1. So if you add 2 plus 1, you're going to get 3. It's an odd number, so you assign a negative sign. For B, you have this B, it is under row 2, column 2. If you add 2 plus 2, it will give you 4, so it's an even number, you assign a positive number. The same applies to a 3 by 3 matrix. The cofactor matrix will be A1, which is given a positive sign, A2 negative sign, A3 will be positive sign, B1 it will be negative, because this is in row 2, column 1, that is odd numbers, so that gets a negative. B2 is in row 2, column 2, that gets a positive. B3, it is in row 2, column 1, that gives you 3, which is odd number, so you give it a negative. So applies to C1, C2, C3. So that's how it will appear. Okay, as if A, B, A1, B2, A2, A3, B1, B2, B3, C1, C2, C3, what we call a minus, you can allocate signs to them, then it becomes a cofactor. Okay, that's what it is. Okay, this is a minor, then you can allocate elements of the minor, the sign, then it becomes a cofactor. Okay, so that's what it is. So here we are. Let's see how we calculate the determinant of a 3 by 3 matrix then. Okay, if we take the matrix which we started looking at, which is in this particular case this one, A1, A2, A3, B1, B2, B3, and C1, C2, C3. What we need to do is you can either take a row or you can take a column. Okay, any vector, either a row vector or a column vector of these particular elements, and then calculate the cofactors for that. So that's what we are going to see happen here. So using that same matrix of A, B, A1, B1, A1, B1, B2, meaning A1, A2, A3, B1, B2, B3, C1, C2, C3. If we can work out with that, we can come up with a determinant of the matrix. Can come up with a determinant of a matrix. So you just get one, either a row vector or a column vector and use the minors of the elements in that particular column vector or row vector. In this case, we look at the first row, which is got elements A1, A2, A3. So as I said, you come up with a minor of that particular row vector. Okay, in this particular, when you look at the A1, it has a cofactor of A, which is found in the first column, first row, first column, so it gives a positive figure. Then you have B2, B3, and then C2, C3 as off the lines of what are indicated off the drawn line. Okay, so A2, again, you have A2 is found in row 1, column 2. That gives an odd number if you add I and J, which is then the number of the row and number of the column. So that gives you 3, which is odd number, so it gets a negative sign. Then you identify what are the minor to that. So you have B1, B3, C1, C3. Equally for A3, it is found in row 1, column 3. So 1 plus 3 is 4. So that's why it gets a positive sign here. And then you identify its minor, which is B1, B2, C1, C2. Okay. So once you have done that, then you can find determinant by looking at these determinants of these particular minors or minors. Then when you find this, you find that it will be A1 open brackets B2 times C3 minus C2 times B3 plus negative A2 determinant of B1 with B, you get B1 multiplied by C3 minus C1 multiplied by B3. Okay, altogether. Then you have also this one is supposed to be plus, okay, plus A3 determinant, you get B1 multiplied by C2 minus C1, C1 multiplied by B2. Okay, so that's what we have. Okay, so when you calculate this one, it will give you the determinant of this matrix A, B, A1, A2, A3, B1, B2, B3, C1, C2, C3, which we started with. That's how you get the determinant. Okay, that's how you get the determinant. Okay, fine. Let's look at how we actually evaluate this particular matrix. We have in this case a matrix where we want to find the matrix is made up of elements 1, 2, 3, 4, 2, 4, 1, 6, 2, 1, 5. That's a matrix. Okay, that's a matrix. So if you look at the column vector for the first row, you are going to have to identify the sign. So number 1, this 1 here, it is found in the first row, first column, so it takes a positive sign. This 2 is found in the first row, second column, so 1 plus 2 is 3, odd number, so it gets a negative sign. This 3 is found in the first row, third column, so 1 plus 3 give you 4, which is a positive, so it gives you a positive sign. Okay, so want to find the determinant of this matrix. determinant of this matrix. So that's what we're going to look at in this particular case. So we have taken 1, -2 as the sign given here. Don't forget, we are looking at the elements +1, there's a +1, then -2, then +3. So you have element +1, -2, +3. Okay, so we find the determinant of these minor. Okay, so what we have is 1 multiplied by 4 times 5 minus 2 times 1, which is still 2. Then we have 20 minus 2. Then here positive times negative is -2. Then the determinant of, we're going to get 2 times 5, which is 10, minus 6 times 1, which is 6. Then plus this other one is 3, and the determinant you get 2 times 2, which is 4, minus 6 times 4, which is 24. So when you simplify this, it will be 1 times 18, which is 18 here. Here it will be, the bracket will be -4, or +4 times -2, which will be -8. Then the last one will be, inside there will be -20 multiplied by 3, which will be -60. So simplify that one, you're going to end up having -50 as the determinant for that matrix. So that's how you calculate the determinant of the 3 by 3 matrix in one way, using cofactors and in calculating the determinant. So when you are looking at the 3 by 3 matrix, you need to understand what is a minor, and then you need to understand what is a cofactor. A cofactor is a minor with a sign. A cofactor is a minor with a sign. So you go through that, what I've shown you, you will still get a determinant of a 3 by 3 matrix. However, I'll show you another simple method of calculating the determinant of a 3 by 3 matrix. For now, that was it. We also look at how do we calculate the inverse of a 2 by 2 matrix. I looked at the determinant of a 2 by 2 matrix. Now we can look at an inverse of a 2 by 2 matrix. So let's say A is a matrix whose elements are A, B, C, D. The first step you need to take is find the determinant of the A matrix. So in this particular case, determinant of A is equal to, you get this one, the downsloping diagonal, which is this one, is going to, first of all, you get the determinant of this one. Let me just start by looking at this one. Determinant, you need to put the symbol for determinant is a parallel, straight parallel line. Okay, that's what we get as a symbol for a determinant. Okay, fine. Then we have to get determinant to be A times D minus C times B. That's the determinant, okay, of this matrix. Second step, we get the inverse of A matrix. The inverse of A matrix is obtained by getting the inverse of the determinant multiplied by the matrix where the downsloping diagonal elements change position. So you can see where A was is taken by D, and where D was is taken by A. Then the upsloping diagonal is maintaining the positions, only that it changes the signs. Here C was positive and B was positive. Now because it changed the sign, C becomes -C and B becomes -B. You get the that when you multiply by the inverse of a determinant, what you are going to get is what is known as an inverse of a matrix A. So let's look at how this is done. Okay, let's say we have, let's find the inverse of a 2 by 2 matrix, which is given by elements 1, 2, 3, 4. 1, 2, 3, 4. Okay, so now step 1, you look at this matrix B. You look at finding the determinant of this matrix. Where you're going to get determinant of this matrix will be 1 times 4 minus 3 times 2, which is going to be negative 2 in this particular case. So we have secured what is the determinant of this 2 by 2 matrix. To get the inverse, you get into the step 2, where you have to find the inverse of matrix A, which is going to be equal to inverse of determinant into the original matrix, which has the downsloping diagonal transposed elements. So where 1 is, it is taken by 4. Where 4 was, it is taken by 1. That's what we see here. Then the upsloping diagonal, they maintain the same position but only change the signs. So here we have negative 3, here is negative 2. So when you multiply this inverse matrix, it becomes more like it's a scalar quantity. So scalar quantity multiplied by matrix, you multiply each element by the scalar. So it will now be going to end up with the first element will be 1 over determinant of A, which we calculated as negative 2. So it will be 4 divided by negative 2. The next one, determinant A is negative 2, so it's 1 over negative 2 times the negative 2. It will be negative 2 over negative 2. Then it will multiply by negative 3. The determinant, inverse of the determinant will be going to give us negative 3 over negative 2. Then we have the inverse of A, determinant A. In this case, we are looking at A not B, A B rather not A. So let me change this one. So we have B. Okay. Even here, it is B. Okay, that's fine. So we have the B there. So that's what we're going to end up with. So the inverse of the matrix B is going to be 4 over negative 2, that's the first element, negative 2 over negative 2, that's the second element on the first row, then negative 3 over negative 2, and then 1 over negative 2, that is the last element in the last row. Okay, that is the inverse of this B matrix. Okay, so now we move on to look at how do you determine the identity matrix of the 2 by 2 matrix. Identity matrix of a 2 by 2 matrix. How do we work out that one? How do we work out that one? Okay, so what we're going to do is look at the same matrix. Let's use the same matrix where we have already calculated the inverse of the matrix as 4 over negative 2 as the first element, and then negative 2 over negative 2 as the second element, then negative 3 over negative 2, that is the third element in the first row. The first row, first element, second row, that first element, then second row, second element will be 1 over negative 2. That is the identity inverse matrix. The inverse matrix multiplied by the original matrix. So you can see here, identity matrix is equal to inverse of B matrix times B matrix. So inverse of the B matrix is what we got here, and the B matrix is 1, 2, 3, 4. So when we multiply these two matrices, rows in 2 columns, we are going to end up with these calculations. So it will be 4 over negative 2 times 1, okay, plus negative 2 over negative 2 times 3. So that will give you 4 over negative 2 plus negative 6 over negative 2. Then the next one will be negative 4 over negative 4 over negative 2 times 2 plus negative 2 over negative 2 times 4. That will give you 8 over negative 2 plus negative 8 over negative 2. You do the same the second row. It will be row in 2 columns. So negative 3 over negative 2 times 1 plus 1 over negative 2 times 3. Okay, that will give you negative 3 over negative 2 plus 3 over negative 2. Then you have the second row into the second column, which will be negative 3 over negative 2 times 2 plus plus positive 1 over negative 2 times 4. So it will simplify to negative 6 over negative 2 plus 4 over negative 2. So when you work out this, you find that this first one, 4 over negative 2 plus negative 2 over negative 2, negative 6 over negative 2, it will end up to be negative 2 over negative 2. Then this 8 over negative 2 plus negative 8 over negative 2, it will be 0 over negative 2. Then you come down here, we have, maybe I put this one in parentheses to help maybe. Okay, to help, we are dealing with these elements. These are the elements we are dealing with. Okay, we're dealing with these elements. Okay, even here we are dealing with this element. Okay, that's what we have. So it will simplify to this, which is 0 over negative 2, and then here is negative 2 over negative 2. So working out this one, negative 2 divided by negative 2, it will be 1. 0 divided by negative 2, it will be 0. 0 divided by negative 2 down here, it will be 0. Then negative 2 over negative 2, it will be 1. So this will be the identity matrix. That will be the identity matrix. Okay, so that's what we have. That's sorted out. We move on to look at inverse matrix of a 3 by 3 matrix. We have looked at how to come up with the inverse matrix of a 2 by 2 matrix. Now I want to look at the inverse of a 3 by 3 matrix, normally written as a to the power 1, or as I've shown you, a to the power negative 1, or simply 1 over a. That is the symbol for inverse of a matrix. Okay, so steps in calculating an inverse of a 3 by 3 matrix. 1. Replace every element in a matrix by cofactors, which is a minor with a sign, as I've already explained what a cofactor is. Then transpose the cofactor matrix, and the result is called the adjoint of a matrix. Okay, then third, you divide the adjoint by the determinant of the matrix. Then you have the inverse of a 3 by 3 matrix. Okay, so let's look at how that is done. Let's look at how that can be done. Okay, we have this matrix, negative 2, positive 2, negative 0, positive 5, negative 1, positive 2, negative 2, 2, negative 1, positive 6. Okay, so we now look at finding the determinant. We can use the first one, the first column, row vector rather, so which is got 2, 0, and 5. 2, 0, and 5. So we find out what are the minors of these particular elements in the row vector, 2, 0, and 5. So for the first one, which is 2, what is the minor? So as I said, where 2 is, you draw a line there and also cross out the column. Okay, what are the elements which are free? There is a positive, there is 2, there is a negative 2, there is a negative 1, there is a 6. Okay, so that's what we have. Okay, so that's what we have in this particular case. So what we do in this particular case, we identify these minors here. These are the minors. Then we come to 0 as well. What we do is we remove, we identify where 0 is. So the row in which 0 is, you mark it. The column in which 0 is found, you also mark it. Once you mark that one, the free elements not crossed by the lines is 1, 2, and 2 again, and then 6. Okay, so the original matrix, okay, before these are already got signs assigned to it. We're looking at the original matrix. The original matrix before assigning the signs. What was it looking like? It had this type of presentation. It had 2, 0, and 5. Here it has 1, 2, and again 2. Then it has 2, 1, and 6. Okay, so that's the original matrix before assigning giving it the signs. You can see, because 2 here is in the first row and the first column, 1 plus 1 gives the positive sign. That's the sign which is given here. 0, it is the first row, second column. So 1 plus 2, it is 3, which is, that's why it's giving a negative sign here. 5 is in the first row, third column. So 1 plus 3 is 4, which gives it, that's why it's given a positive sign here. If you look at negative 1, this first one here, why was it given a negative? Because it was like positive 1, because it's found in the second row, first column. So 2 plus 1 is 3, that's why it's given a negative sign here. The original matrix here, 2 was here. So 2 is found in the second row, second column, second row, second column. So it's 2 plus 2 is positive, that's why this 2 is given a positive sign here. This other 2 in the row, but in the third column, it is in the row number 2, column 1. 2 plus 1, row number 2, column 3. So row number 2, column 3, that is 2 plus 3, which is 5. That's why it's given a negative sign here. This 2 is in the third row, first column. So 3 plus 1 is equal to 4. That's why it's given a positive sign here. 1 is found in the third row, but second column. So 3 plus 2 is 5, which that's why it's given negative 1 because an odd number. Then 6 is found in the third row, third column. 3 plus 3 is 6. That's why it's given a positive number. Otherwise, the original matrix was 2, 0, 5, 1, 2, 2, 2, 1, 6. So we are looking at this. So we are looking at having taken the row vector of 2, 5, 0, 2, 5, 0 elements. Okay, so that's what we have. So 2 is given a positive. That's what you have picked. And what is the minor? So for 2, you get these 2, and then you get the row which is also this one. So you cancel the elements falling on this particular, falling on the lines, leaving you with 2, 2, 1, 6. So 2, 2, 1, 6. Okay, 2, 2, 1, 6. Okay, 2, 2, 1, 6. So that's what we have. Okay, that is what we have. So if that's the case, then what we do, we identify those particular minors. Okay, so you have, in this particular case, you are going to have positive, okay, and then you're here, you are going to have this one will be for 0, you cross out this one and that one, you're going to have 1, 2, 2, 6. Okay, 1, 2, this one is like that, 2, 6. The last one, 5, you cross out this row, and this column. You have 1, 2, 2, 1, 1, 2, 2, 1 as positive values here. Okay, positive values here. These are positive values. Okay. Okay, fine. Then we work out the determinant of this. So it will be 2 multiplied by 2 by 6, which is 12, minus 1 by 2. Okay, 1 by 2, which is still 1. Okay, so it's supposed to be 1 here. 2 times 6 is 12. 1 times 2 is 2, minus here. Then you have the next one, which is 0 into 1 times 6, which is 6, minus 2 times 2, which is 4. It's supposed to be just 4 here. Okay, then plus, we have 5 multiplied by 1 times 1, which is 1. Supposed to be 1. Then minus 2 times 2, which is 4, which is that much. Okay, so what we get now, we have 2 into 12 minus 2, which is supposed to be 10. Then 0 times any number times 0 is 0, so we have just plus 0. Then we have 5 times 1 times 1 minus 4, which is negative 3, which is basically negative 15. Okay, so that would be 5 times negative 3. Okay, this one is 0 times, maybe let me just complete, 0 times 6 minus 4, which is simply 2. okay, which is 2. So when you evaluate this one, it will give you 20 plus 0 minus 15 minus 15, which is going to give you basically 5. That's the determinant of this 3 by 3 matrix. That's how you calculate the determinant of this 3 by 3 matrix. Okay, so I've shown you how to calculate determinant of the 3 by 3 matrix using this method. Okay, using this particular method. Okay, so now what I want to show you is again how do we calculate the inverse of a 3 by 3 matrix. We have just looked at how do we determine the determinant of a 3 by 3 matrix. We want to know how do you determine the inverse of a 3 by 3 matrix. Inverse of 3 by 3 matrix. So what will happen is that we have to create a matrix of cofactors. A matrix of cofactors. So that's the first thing. Replace every element in the matrix by cofactors, that is minor with a sign, and then transpose the cofactor matrix, and the result is called the adjoint matrix. Then you divide the adjoint by the determinant. So we have already calculated the determinant. We go look at this particular matrix, which is a 3 by 3 matrix. This one, which I have created here. Okay, so now we have to find what are they. For each element, replace them by cofactors. So if you look at that, we are going to have a matrix with a lot of these items. So we have this whole matrix, this mod matrix, which are going to give you the first one as we represented. I just make up adjustments here. Okay. Okay, so meaning that this one you are going to have 2 times 6, which is 12, minus 1 times 2, which is 2. Okay, then the next one will be 6, which is 1 times 6, which is 6, minus 2 times 2, which is 4. Post 4 here. The last one will be 1 times 1, which is 1, minus 2 times 2, which is 4. There will be a 4 here. Okay? There will be a 4 here. Okay? Then we're going to have the next one, which is in this particular case, there's certain adjustments here. Okay. Certain adjustment. We have 0 times 6, which is 0, minus 1 times 5, which is still just be 5 here. Okay. The next one will be 2 times 6, which is 12, minus 2 times 5, which is 10. Positive 10. The next one it will be 2 times 2 times 1, 2 times 1, which is 2, okay, minus 2 times 0, which is 0. We get to the next one, which is 0 times 2, which is 0, minus 2 times 5, which is 10. We get to this other one, 2 times 2, which is 4, minus 1 times 5, which is 5. The last one will be 2 times 2, which is 4, minus 1 times 0, which is 0. So we have calculated, we have used the cofactors. We have first of all the minus, then assign or allocate signs. A minor with a sign is a cofactor. So the first element is this one is in row 1, column 1, so it takes a positive. This one is in row 1, column 2, it takes a negative. This one is in row 1, column 3, it takes a positive. This one is in row 2, column 1, takes a negative. This one is in row 2, column 2, takes a positive. This one takes a negative, and so on and so forth. That's what you have created. Okay, that is what we have created. Okay, so move on. Okay, we move on. So what do we derive from this one? So this one basically will be a 10 followed by a 2 followed by followed by a negative 3, 10, then negative 10 to negative 3. That's how it is. 10, 10, this will be 10, 2, negative 3. Okay, then we have the next line. What will be the next line? The next line will be, let's get back to it. This one will be negative 5 to 2. So it will be negative 5 2 and 2. Okay, so what will be the third row? Third row is this one. 0 minus 10 is negative 10. 4 minus 5 is negative 1. Then 4 minus 0 is 4. So it will be negative 10, negative 1, 4. Negative 10, negative 1, 4, as it is. Okay. So now, then we consider the signs. Okay, consider the sign. The first one, this one assumes a positive because it is in row 1, column 1. This one assumes a negative because it is in row 1, column 2. This one assumes a negative because in row 1, column 3. Okay, then this one is in negative 5 is in row 2, column 1. Row 2, that's negative, so it becomes positive. Okay, row 2, column 1, so it becomes positive because there is already negative here, so negative times negative becomes positive. Row 2, column 1. Then this one is in row 2, column 2, so it maintains still positive. Then this one is in row 2, column 3. It's negative, so it takes a negative sign. Okay. Then we have the last one, last row. Here it is in row 3, column 1. It's positive times negative is negative. Then this one is in row 3, column 2, negative. Negative times negative, positive. Then this 4 is in row 3, column 3, positive, so it remains positive. Positive times positive. Okay, so now we have cofactors with, that is minus with signs assigned to it. So the next thing we do is we transpose these cofactors. So we transpose these cofactors. So the row becomes a column. So this 10, negative 2, negative 3. So we have 10, negative 2, then negative 3, then you have the next one will be five, which is a 5 here, then 2, then negative 2, negative 2, then you have negative 10, 1 and 4. Okay, so how do you know that you have correct position? So this 10 here, the I, which represents the number of the row, is 1, the J is 1, column 1, row 1, column 1. You transpose, it still becomes 1, 1, so that's why it maintains the same position here. For this 2, it is at a position of row 1, column 2. So to transpose it, it will go to row 2, column 1. Row 2, column 1. That's why you find negative 2 here. So you swap the J and I. Okay, you swap the J and I. The J in the first original matrix, this one has 1, which represents 1 first row, and 1 again, representing the column. So when you swap, it still be 1, 1. But this one here, which had I as 1, J as 2, to transpose it, J becomes I and I becomes J. So as it is here, negative 2 is at position row 1, column 2. When it is transposed, it will go to row 2, column 1. So that's why you find it here. This 3 is in row 1, column 3. So it will go to row 3, column 1. That's why it finds here. So that's how you transpose. So when you transpose a minor with a sign or a cofactor, it becomes an adjoint of a matrix. So this is an adjoint of a matrix because you have transposed the minor with a sign, or you have transposed the cofactor, okay, with a sign. So now, once you have transposed this, then the next thing you do is divide by the determinant which you calculated as 5. Determinant which you calculated 5, you divide the adjoints by determinant. So this one will be 10 divided by 5. That's what we found, 5. Then this one will be 5 divided by 5. Then this one will be 10 divided by 5. Okay. Then this one will be it will be 2 divided by 5, negative 2 divided by 5 divided by 5. Then here it will be positive 2 divided by 5. Remember the determinant still maintained. Then here it will be 1 divided by 5. Then here it will be negative 3 divided by 5. Then this one will be negative 2 divided by 5. The last one, it will be 4 divided by 5. Okay, that will be the inverse of the matrix. That will be the inverse of the matrix. Okay, so that's how we calculate the inverse of a 3 by 3 matrix. Okay, so now we look at how do we solve the system of equations using matrix methods. Okay, there are two methods that can be applied to solve a system of equation, namely Cramer's rule or Cramer's method and inverse method. Let's see what we can discover by learning through this particular session. Cramer's method. The procedure is you write the system of equation in a matrix form, and then show the vector of the unknown, and also write the coefficient matrix, and then write the solution matrix. Basic procedure rather. Okay, so let's proceed. Cramer's rule. I'm going to cite or illustrate this particular explanation using a practical kind of situation. As an example, let's say that we want to use Cramer's rule, and here is a situation. In the example, the production of a particular computer component is done in 3 stages, taking a total of 7 hours. The second stage is 1 hour less than the first stage, and the third stage is twice as long as the second stage. You are required to calculate how long each stage of production will take. Okay, so you can actually look at this and reduce it to mathematical statements as given here. So let A equal to the number of hours of the first production stage, B the number of hours in the second stage, C the number of hours in the third stage. Then deriving the mathematical statements, then we can say that the total production time is equal to A plus B plus C which is 7 hours as guided in the example. Now, since the second stage is 1 hour less than the first stage, then we can say B, which is stage 2, is equal to, is the same as A minus 1, okay, because we are subtracting 1 because we are told B is 1 hour less than the first stage. So it can be stated as B is equal to A minus 1. Again, given that the third stage is twice the second stage, then, and we know that B the time is the second stage, so it means that you can get the total number of hours C by looking at twice the hours of B for C. So C is equal to 2B. So that's what is given in this particular scenario. Okay, so let's continue. Now we can formulate a matrix, okay, where we have A plus B plus C is equal to 7. Then A minus B is equal to 1, because we know that B is equal to A minus 1. So when you rearrange it, you end up having A minus B is equal to 1. The last is that 2B or C is equal to 2B. C is equal to 2B. You can rearrange it and it will come to be 2B minus C is equal to 0. Okay, so we have a system of equations. Now we can extract the coefficient matrix and the solution matrix for this. So original coefficient matrix, we have for A, variable A, there is 1 coefficient there. For variable B, there is 1 coefficient. For variable C, there is 1 coefficient. For the next one, A, there is variable A, coefficient 1. Variable B, the coefficient -1. There is no C, therefore we have coefficient 0. For third one, there is no S, therefore we have coefficient 0. There is coefficient of B is 2. Coefficient of C is -1. So we have generated the original coefficient matrix as 1, 1, 1, 1, -1, 0, 0, 2, -1. Then for the solution for variable matrix, we have 3 variables, A, B, C. Those are the unknowns, A, B, and C. So we have this variable matrix, A, B, C. The solution is a matrix of 7, 1, 0. 7, 1, 0, that is a solution matrix. So we have the coefficient matrix, variable matrix, and solution matrix. Then we are ready to proceed. Okay, so I'm going to show you how you can use a shortcut to come up with the determinant of a 3 by 3 matrix. Okay, so we have derived our original matrix as 1, 1, 1, 1, 1, 1, -1, 0, 0, 2, -1. So what we do is, if you want to solve for A, you replace the first column by the solution matrix values, elements of the solution matrix. So where 1 is, there will be 7. Where this 1 is, there will be this 1. Where this 0 is, there will be 0. So that we end up having 7, 1, 1, 1, -1, 0, 0, 2, -1, and find the determinant of that. Then divide by the determinant of the original matrix as it was before the replacement of the first column by the solution matrix. We had 1, 1, 1, 1, -1, 0, 0, 2, -1. So you also find the determinant there. So the simple way of calculating the determinant of the 3 by 3 matrix is to write the elements of the matrix, in this particular 7, 1, 1, 1, -1, 0, 0, 2, -1. So end up here. Then replace or repeat the 2 columns in this matrix, you repeat, that is 7, 1, and 1, negative 1, and 0, 2. So now, once you have done that, you identify, you draw lines whereby you have a off diagonal matrix which has got 1, 2, 0. So you start from the end here, you draw a line through 7, negative 1, and negative 1. The next one, again, a line through 1, 0, and 0. Another line through 1, 1, 2. These assign them positive symbols or positive sign. Then you go to the diagonal, upsloping diagonal, starting from the corner here, 0, up through to through negative 1 and 1, assign the negative sign. The next upslope diagonal is 2, 0, 7. The last is negative 1, 1, 1. So what you do is you multiply these elements in these ruled lines, along these ruled lines. So you have 7 multiplied by negative 1 multiplied by negative 1. So that will be positive. So it will be positive, open bracket, 7 times negative 1 times negative 1. So 7 times negative 1 is negative 7. Times negative 1, it will be positive 7. Then plus 1 times 0 is still be 0. So 7 plus 0, it will still be 7. Then plus 1 times 1 times 2, it will be 2, times 7, it will be 14. Okay? Then minus 0 times negative 1 times 1, any number multiplied by 0 is 0, still 0. Again, minus 2 times 0 times 7, still 0, so it's 0. Then you have negative 1 times 1 times 1, which will be equal to, it will be equal to negative 1. Did I write properly? Let me see. Okay. Okay, let's see how this is done. So we are looking at these calculations so that we follow it through. So in this particular case, what do we have? We have 7 times negative 1 times negative 1. So we have 7 positive, seven times negative 1 times negative 1. Then plus. Okay, so we are here. So 7 times negative 1 times negative 1. That's what we have here. Then plus 1 times 0 times 0. 1 times 0 times 0. So 1 times 0 times 0. We're going to have 1 times 0 times 0 plus. Okay, what do we have again? We have 1 times 1 times 2. 1 times 1 times 2. We're going to have 1 times 1 times 2. It is 1 times 1 times 2. Okay. Okay, fine. So what we have? We have then the next one is subtraction. We start looking at the others, which is 0 times negative 1 times negative 1. So 0 times negative 1 times negative 1. 0 times negative 1 times negative 1. Okay, again negative. We have 2 times 0 times 7. 2 times 0 times 7, I believe. Okay, let's check. 2 times 0 times 7, correct? Then we have minus again. We have negative 1 times 1 times 1. Negative 1 times 1 times negative 1. Let me just check. Negative 1 times 1 times 1. Negative 1 times 1 times 1. Negative 1 times 1 times negative 1 times 1 times 1. Okay. So evaluate this one. This will show you this one will be positive. 7 times negative 1 times it will be 7. Then plus 1 times 0 it will be 0. Plus 1 times 1 times 1 it will be 2. Then minus 0 times negative 1 times 1 it will be negative 0. Then 2 times 0 times 7 it will be 0. Then last is negative 1 times negative times 1 times 1 to be positive 1. Okay, so this is what we have. Resolve this one. It will be equal to 2 plus 2, that's 9 plus 1, that is 10. That's how you get 10 there. So the determinant will be on the top, it will be 10. So that's what you get as determinant on the top to be 10. That's why you have 10 here. If you do the same here, you find that determinant below here will be 4. So you end up A is equal to be 5 over 2 in simple terms. So that's a solution for variable A. That's how you solve for A. Okay, you go look at how do we solve for B in a similar manner. For B, the column will be the middle one, the second column, which you are going to replace with the solution matrix 710. Okay, then the first column will remain the same, the third column will remain the same. Work out this one, you find the determinant will be 9 over 4 because the bottom line does not change, so it will still be the same determinant, means that B is equal to 3 over 2. 3 over 2. Then you go to solve for C in a similar manner. You replace the third column on the top here by the solution matrix 710 and then find the determinant in a similar manner, and the determinant for the bottom one is the same, it does not change. You find that it will be 12 over 4. 12 over 4 simplified, 4 into 12 is 3, so C is equal to 3. So that's how you solve for this particular simultaneous equation in 3 unknowns using matrix method. That's how you solve using the matrix method. Okay, so I want to also introduce you to how to solve the inverse and identity matrix. Okay, for inverse matrix of a 2 by 2 matrix, this is how you calculate it. The formula is, if M is the matrix A, B, C, D, the inverse of M will be written as M, we use calculator, yes, M, which is equal to 1 over the determinant of A times, which is A times D, as we saw how to calculate the determinant of a 2 by 2 matrix, A times D minus B times C. Then into the original matrix, you transpose the elements in the diagonal matrix, which is downsloping. Where A is, it's taken by D. Where D was, it's taken by A. Then the upsloping diagonal matrix, you just change the sign. So when you multiply the inverse of the determinant into the transposed diagonal sloping, downsloping matrix elements, and then the change sign of the upsloping matrix elements, then you are going to get an inverse of a 2 by 2 matrix. So let's say you have a 2 by 2 matrix in form of 4x plus 3y is equal to negative 5 and 7x plus 5y is equal to negative 11. Okay, how do we get the inverse of this material matrix, coefficient matrix? That's what we look at. Okay. The procedure, you write the equation matrix equation, multiply each side by the inverse of the coefficient matrix, the result will be identity matrix multiplied by the variable, and interpret the solution. So that's how you're going to get the solving of the solution for a simultaneous equation in 2 unknowns. Okay, in this particular case, what we have is to derive the coefficient matrix of this matrix which you have here. Okay, so coefficient of x 5, coefficient of x here 7, coefficient of y here 3, coefficient of y here 5. So that's what you have here. You have 5, 3, 7, 5. So this is the coefficient matrix. Then the variable matrix, you have x and y, and then you have solution matrix equal to negative 5, then negative 11. So this is the solution matrix. So you're seeing okay. Yeah, the solution 5x plus 3y is negative 5. Solution 7x plus 5y is equal to negative 11. So that's what we have picked, okay, to be the solution matrix. So negative 5, negative 11. So we find the inverse of the determinant. The determinant of the original matrix 5 times 5, which is 25, minus 7 times 3, which is 21. So inverse of that's 1 over that, which will be into the original matrix. You transpose the downsloping diagonal, So when the 5 and 5 swap, it will just look the same. The 5 which was here goes there, 5 which was comes here. But these upsloping elements in the diagonal just change the sign. So it was positive here, it becomes negative. It was positive 3 here, it becomes negative 3 here. So when you multiply the inverse of determinant into this matrix, creation the transposed elements, you are going to get an inverse matrix. Okay, so that's what we're going to look at. So if you simplify that one, okay, which is 1 over 4 into that, you're going to and you multiply this one to the matrix on both sides of the equation. So you're going to have this inverse matrix into the original matrix times the solution, the variable matrix. What you do this side, this inverse matrix, you also multiply the solution matrix by inverse matrix. So that's what you have done here. So the inverse matrix is 1 into 5, matrix 5, negative 3, negative 7, 5. Even here, 1 over 4, 5, negative 3, negative 7, 5. So these are inverse matrix. So you multiply both sides of the equation, and what you get? You get this one reduces to, when you multiply the inverse of matrix with the original matrix, gives you identity matrix. Identity matrix will give you a matrix with the diagonal downsloping ones and the any elements out of the diagonal downsloping is zeros. That is an identity matrix. Then multiply by the variable matrix. If you multiply this identity matrix to the variable matrix, to give you the variable matrix itself. So it will come to x, y, and then this reduces to 8 over 4, which is 2. This one will reduce to negative 20 over 4, which is negative 5. So they are now equated. So x is equal to 2, y is equal to 5. So that's what it is. That when you have solved the system of equation in two unknowns, okay, using the this method, matrix method. Okay, thank you for having listened to this. Okay, next time we're going to look at is how do we determine the inverse matrix with a 3x3 matrix, as well as solve for maybe 3 unknowns again. Okay, so that's what we have. If any questions, you have any questions, you can drop a line, and I will be more than glad to assist you to understand what I've covered today. Otherwise, please don't forget to subscribe to my channel and also like my videos. Bye for now.